Very good. It calculates the area under the curve. So if you now look at this integral, it will calculate the area under a curve of mu of omega, function about time, and multiply it with some weight function that is shifted on the omega prime scale, and it will calculate the area under that curve. If you would sketch this 1 over omega prime squared minus omega squared function, so that is the blue, the yellow, the light blue part, it would look like this. So what the integral does basically is it takes a function with this shape, puts it at a certain frequency position omega prime, at a certain position omega, and multiplies the two, so the omega function, the weight function with the mu a function, and then calculates the area under that curve. So how would that? Can we now think of how that would look like if we have, let's say, an absorption spectrum? So in green, the blue, but if we have an absorption spectrum that looks, for example, like this. So with one peak. Here on the horizontal axis, we have omega. In this case, normalized by some center wavelength that is not so important. What would happen if you would calculate this integral? For example, here at this frequency, 0.4. So what would the physical way of calculating that integral do? Yeah, so you have this spectrum. You multiply it with this function to calculate the area under that function, and that is and the output. That is the result. Would it matter? So this function is symmetric. That is on purpose, of course. Would it matter if you calculate here or here?
Right. Is that your peak is on multiplied being a positive or negative value?
Yeah. Exactly. So this function is symmetric. With this function, the weight function is not symmetric. So it will matter if you do it here or there. Yeah. Yeah. Specifically, so this is not a not a very good drawing. What you see here in black is this weight function, because it is on the same scale. You cannot really see the details, but this is still the function that has that dips from this side, then shoots up, and then decodes. So what the integral calculates is taking the black function, the black function and the blue function, multiplies them together, and calculates the area under the resulting curve. And as you can see, that if we are here, positioned here, then the area under the product is going to be higher on the positive axis, on the positive values, right from the right side from the analysis frequency than on the left hand side. So you will have smaller negative contributions, higher positive contributions, which will result in a higher value of that integral. That integral in this case calculates f omega. If you do it the other way around, or on the other half of this absorption peak, then the situation is just reversed. So the weight function is still the same. So it dips here, then shoots up, and indicates here again. That's symmetrically, but you will have larger contributions here. In this case, now on the negative side, than from the positive side, and that will result in a lower value. I have a simulation that I will show you. So this is that same graph. So what I want to calculate is first of all is n of omega. So just this this Kramers-Kronig relation for the real part of the refractive index in terms of the absorption function. With that, the absorption spectrum is given there. So it's the top graph, mu I of omega. What the integral does is again multiply this weight function with the spectrum and then calculate the area under it. And you have to do that for each and every frequency, for each and every step. So the weight function is going to move. Start from the left of the figure, and then we'll move to the right. And each time we will just calculate the area under that curve. Calculate it. That is what you're going to see in this graph. That will be as a function of frequency. The physical measurable part is wavelength, color. So I'm also going to plot that as a function of wavelength, which is proportional. It's a little bit hard to see in this case. Proportional to 1 over the frequency. So there we go. Calculating the integrals. Now we'll run it again. So you can see, so the weight function then just moves over the whole spectrum. The weight function is very narrow, but it moves over the whole spectrum. You calculate the area under the product. That's what the integral does. And the result is displayed there in red as a function of frequency omega and as a function of 1 over frequency wavelength. Okay, what do you know?
First of all, the second plot is goes from 0 to positive values, but it makes sense because it's inverse. The wavelength is 1 over omega, so it makes sense that it's a small bigger value to smaller ones.
Yeah, that's true, and it also means that the reciprocal relation between wavelength and frequency means that it is a little bit stretched. So it is not as symmetrical as it is in this case. Any other thoughts? Things that you notice?
This jump in the second, that's just an indication of color, right?
Jump in a second.
Yeah, unfortunately. And in the middle,
This?
no, the one above, there's like a red bump on the right, but that's like the color of the bump.
Like the legend.
Oh ja. Oh god, ja, inderdaad. Oké. I'm not a very good programmer, so I didn't think of that. Okay, yeah, good. Good catch. Nice, good catch. Okay, so I'm not a good programmer, but I managed to have a checkbox there that says 2 absorption bands. So what it will show now next is you can see my mouse. Hopefully, is a new little bump here. And then it will do the same calculation. Can you now already predict how these 2 graphs are going to look like? Giving the second one. So what we see now is that if we have one peak around the center, the center of the peak, we have first an let's call it it swings up a little bit and then it swings down a little bit. I mean, you could even say it looks like a derivative. It's not entirely wrong to think that way. And then if we scale to wavelength, then it gets all a little bit stretched and compounded. But the first thing is indeed to look at frequencies. So let's put that on. So there's the second done. So that's not scaling. So we're running through all the frequencies, calculating all the integrals, calculating all the areas in the curves. And see the result there. So if you now compare, so again the question is what kind of features do you see? What kind of
And the second one, that should be mirrored, right?
This one mirrored with respect to that one, you mean, or
No, just because it's from it's starting at 5, and if you like, so it's like the axis is on the other, starting on the other side, but in actual, if you put on the other side.
yeah, so the axes are inverse. So this graph is calculated really on the omega axis, and this one is because of the inverse axis. So it starts from that point. Is that what you mean? Or yeah, so that's true. That is a little bit, but so this information is completely the same. The only thing that I changed here is the horizontal axis. So the way it is plotted, the calculation is just the same. What I notice, what I think is an important thing to notice is that you have a small oscillation and a large oscillation. So this is basically a small ripple. This is a larger ripple, and they correspond to the magnitude of the peaks in the original spectrum. So that would suggest that if you have an absorption spectrum with a large absorption coefficient, if you have an absorption peak, an absorption spectrum with large peaks, that will give larger differences, larger oscillations in the refractive index spectrum than compared to the small ones. Also, they are centered in the same way. So if we have an absorption peak with the center, so let's say at 1 here, resonance, then the oscillation in the complementary spectrum, in the refractive index spectrum, will be also centered at that wavelength. The oscillation will be the gradient of the oscillation, if you want, will be maximum there. This is what we saw, so I'm going to skip that. This phenomenon does explain a few physical observables in real life. So glass, for example, has a pretty high absorption band in the UV wavelengths. You don't get a tan if you're sitting down in glass. So much of the UV light is being absorbed. If we look at BK7 is a type of glass, but that is a common type of glass. If you look at the transmission of the glass as a function of wavelength, here it is in micrometers, so it is always it's a little bit convoluted, but so that is 300 nanometers. That is in the UV part. You cannot see that, and this is for 50 nanometers. You see that the transmission in that wavelength range is not that high, just in the lower range, which means that the absorption coefficient of the transmission is not high. That means the absorption is actually high. So the absorption coefficient is high. So there is an absorption peak in this 300 to 400 nanometer wavelength range photons. So that would look like just like the graph that we just saw. So something like an absorption peak at let's say 400 nanometers, and that would translate into so again centered at 400 nanometer. It would on a wavelength axis it would dip, then go up, and then have a shape like this. The effect is that in waves, so this would be around 400 nanometers. If you would look further at longer wavelengths, the result would be a decaying function of wavelength. That is exactly what you see. That is exactly what you see. If you look from 400 nanometers up to, let's say, 1600 nanometers, you see that the refractive index, so the conjugate part of that absorption coefficient decreases. That's glass. It also works for water. It also works for blood. I'll get to that in a moment. So a question for you, just to see if this lands a little bit. This one actually already showed, so that is it's a pretty flow. So can you now sketch how? Let's do it anyway. Can you now sketch how the spectrum of n, the real part of the refractive index, would look like when this is the absorption spectrum, or the spectrum of the imaginary part of the refractive index, and also the question the other way around. If this is the real part of the refractive index, sketch how the absorption goes. I'm using the word sketch here deliberately because I don't expect you to give a quantitative answer. That is very difficult because of these integrations. But just looking at oscillations, looking at the peaks, looking at the shape of the curves, can you estimate how it will look like? You can also just yell stuff and write it on the board. That's all.
Probably the first one looks like the one we just saw.
Yeah.
It's a little bump and then a second time.
Yeah. So I mean that's also mostly the words I was looking for: a little bump and a higher bump. And this one. So that basically then we're reasoning the other way around. So if you take a look at so we had if we analyze the top graph, then we know that if there is peaks in the absorption spectrum, we'll see oscillations in the real part of the refractive index spectrum. if the absorption peaks are higher than the oscillations, will have a bigger magnitude. So now translate this back. So now looking at this one. So how many oscillations do you see? Yeah, I would say two as well. So down, going down, and then up, and then immediately after that again going down, and then up again. Okay, so two oscillations would correspond to absorption. Which one is higher? Yeah, second one is higher. Yeah, so that would be my conclusion as well. And then the last, and that's a little bit of a trick question. If we have a downward trend going here, could that imply anything?
Slowly going.
Yeah.
It will get smaller, it will get smaller, like get symmetrical.
Now, what I think it means is that so what you see is that if you're on the higher wavelength on the higher wavelength side of a absorption peak, so you have an oscillation centered around the absorption peak. If you're looking at longer wavelengths, then generally the refractive index decreases. See that here a little bit, of course, then it is compensated. See that here a little bit. So this trend is really going downward, then it would suggest to me, I think that there is a huge absorption peak living here that basically pulls the whole thing a little bit asymmetrical. Does it make sense? Okay. So let me try to write it down. So I think what the data shows is that there is a small absorption peak at some wavelength, and then a little bit bigger one at a longer wavelength. That would give rise to this graph. That is what we just discussed. But I think what is implicit here, and what is not entirely shown, is that there is a huge absorption peak even at smaller wavelengths, and that causes the whole trend going down. I'll give you. I'll give you this is what we just discussed this, so that is fine.
Question.
Yeah, no.
If you go one slide back, I'm a bit confused. Why is this? I think it makes sense that the peaks are positive, but if we just look at the final peak, it first goes down and then goes up. So I feel like I understand that the peak actually needs to go down instead of up. You sort of understand what I mean?
A little bit, I think, but
because if we, in the first example, if we only had a normal peak, one peak, and if we go to the relation, then it's first goes up, then to the 0 point, then down.
yeah, but that was on the. Yeah, that's the tricky part. That was on the frequency axis.
Okay.
Yeah.
Then it shifts. Oh, yeah, that makes sense.
Yeah, I should be more careful about explaining it. So all of these examples and even what now is again hidden behind the bar is on the wavelength axis. So it is inversely yeah. So so if you look at and eventually. So the mathematics work out best if you do it on a frequency axis. So that is why most of these calculations are done on the frequency axis. But in the end, what you measure, of course, is wavelength, is a color. That's the physical thing that you can measure. So an absorption spectrum on a wavelength axis with some peak and some wavelength here will translate into some oscillation in the real part of the refracted index spectrum. It first goes down, then goes up, and then goes down. I do have another question for you, something that you can try to calculate for a couple of minutes. So let's again look at this equation, at this integral, and the obvious, the glaring problem is that we need to know. So we want to calculate the refractive index at one frequency. We still need to know the absorption coefficient over all the other frequencies to calculate the flash. Now suppose that we know by some calibration measurements, by some experiment. Now suppose that we know the real part of the refractive index at some frequency and of dubbed omega z. Can you give me an expression for what's then so-called what's then called the subtractive Raman relation? So n of omega minus n of omega 0. So if you just fill in, basically what I'm asking you is, can you just fill in this equation n omega 0? And then we have the expression n of omega. Combine these two equations into something that makes life a little bit. I'll give you a couple of minutes for that. And again, if you want to do it on the blackboard, that's perfectly fine with me. Any thoughts on that? So what happens if you write this same equation, but then for omega 0?
Just change the omega and omega 0.
Yeah.
And then do the
yeah.
structure.
It's a little bit, yeah. Of course, that's right. That's what you do, and then if you then so the next step would then be to write an expression for n omega minus n omega 0.
Yeah, you will use the 1
Yeah.
at the beginning, and then inside the integral you will have the subtraction between the two fractions.
Yeah. So the integral still runs over omega prime, so you can combine the two integrals. That really is all that there is to it. And so this would then be so in blue would be the omega 0 part, and in black here is the omega part. So you would substitute omega for omega 0. You would lose the 1, the factor 1. And you could combine it into a single integral, which now has mu a this function of the dummy variable prime. Of course, that stays the same. And then these two weight terms are now here within the squared brackets. You can expand this this equation by cross multiplying. Sure, you can do that. So I'll work that out too much. Like this, still with an omega 0 in blue and the other term in black. And if you then recombine, then the resulting equation would look like this. So you would have n of omega now being n omega 0 plus some term that is dependent on omega 0 and still an integral term. Still a dispersion relation, still an integral relation that depends on both. So what's the benefit of what we just did?
The weight function is bigger, so we have a sharper.
Yeah. That's a very important. That's a very important benefit. So we started out with omega squared minus omega prime squared, which was this dipping, then increasing, then decreasing function. But now by multiplying it with this term, it gets much narrower. So the calculation of that integral, which we still need to do numerically, gets easier, gets more precise. So that's one big benefit. Is there another benefit? The other benefit is also painted blue here. We can do a measurement. We can do a calibration. We can actually try to measure the refractive index at some omega at some wavelength and use that to scale the whole curve up and down. And now we're getting back to the first curve that I showed you, which had these data points in there. This is exactly what we did. We did a very precise. We tried to do a very precise measurement at a given wavelength and use that to scale the curves to their right value. This is what you just said. Much narrower. You get much better weighting and a much better integration. Okay. A few remarks before we have a break. So let's. So what do I want you to know from us? There's a lot of math involved, and I'm not expecting you to reproduce that math. I think it's fun, and I think it's good to expose you to that. So I just did that, and we'll talk about later about if that is real or not. But there are a few giveaways or a few takeaways that relate to tissue, to the light tissue. So the first, if there is a large absorption peak in the UV wavelengths. So what are the UV wavelengths? 300 nanometers, 400, not more than that, but that is fine. If there is a large absorption peak there, then that will lead in general trending to a decrease in the real refractive index in visible wavelength ranges. So from, let's say, from 500 to 800. So a peak here, there's go here, would lead to a decrease there. We can apply that to water. 70% of us is water. So 70% of your exam question is water. Then you pass. The real refractive index, the real part of the refractive index, is key to understand or to calculate light scattering. So absorption is the absorption spectrum of water is pretty well known. It is something that you can do experimentally quite easily. You can also look it up. And from this formalism, from this relation, you can calculate it. You can calculate the real part of the refractive index, and it is one of the most important values to know if you want to calculate light scattering from tissue. The other important part of light tissue interaction is blood, is hemoglobin, and it is also key to understand scattering by red blood cells. I'll give you a few examples. This is the complex refractive index of water on a wavelength axis. So you can see here that there is the red part is the imaginary part. The imaginary part is related to the absorption coefficient. So you can see here that it's a log scale that in the range between 100 nanometers and 1 micrometer. So that is roughly, very roughly, the visible range, that there is a huge dip in the imaginary part, which means that there is a huge dip in the absorption coefficient, which means that we can see through water. Of course, there is some peaks and some oscillations that are associated with the configuration of water itself. But that is the imaginary part. If you now look at the real part, that is in this case, I think, also a measurement. But you could also, what we could also do is take this imaginary part, do this whole Kramers-Kronig relation calculation, and calculate the real part, and we'll see that it matches, that it's exactly the same. And we can zoom a little bit in, for example. So this, the graph top left is the same as the graph that we had before. Here is the real part of the refractive index now from a wavelength range of 400 to about 700 nanometers, and we see that it decreases with wavelength, and that is due to this big absorption peak at about 100 nanometers. One tricky thing about this graph is that it is plotted here for different temperatures. You see a small temperature dependence occurring here. What does that imply for the absorption curve? It's going to be temperature dependent as well. So then the mathematics equate or correlate these two curves together, and even though we have to be sure that we can measure them over a large range or as large a range as possible. If this one is temperature dependent, then the absorption coefficient is going to be temperature dependent as well. And that's true. That is something that is measurable. That was water. This is blood. So this is again the same version of the graph that I've shown you now a couple of times. So the absorption coefficient of oxygenated hemoglobin and hemoglobin is very, very, very well known. So that is just something that you can take from any website. There is not much controversy there. You can run that through this kind of Kronig equations, and then end up with the graph that's shown there on the top right. By the argument that I tried to make with for the subtractive relations, because we do not know the absorption coefficient from 0 to infinity. We only know it basically from this in this range. So we need some reference measurements. So these are included in that graph. They are these data points. It would get better if you would use more data points, but that was not feasible at the time. But still, the result of that numerical theoretical approach is given in this. The graph here is a little bit of an extension of that approach. So the wavelength range is a little bit longer. We just simply had a little bit more data to work with. These two in color are still the numerical results. These are calculations, so theoretical results. In black, we have two measurements. So one is for plasma, so the suspension that red blood cells are actually living in. That is just as a kind of a reference. And a group in Germany actually managed to measure the real part of the refractive image. So they got these results given by the blood lines. So this is our theoretical calculation. This is the actual real life measurement. What is the? Is it good? Is it bad? Is it ugly? What do you notice? What do you think? Yeah. Yeah, so I was so happy with that. So they have the same oscillations at the same positions at the same moment. So obviously the values are not the same. That was a little bit disappointing, but not it doesn't. I don't lose any sleep on that. The difference is not that.
Is this also like corrected with measurements as well?
Yeah, so this one is so this one the colored ones are actually the same as the top one, so they are corrected with measurements. This one is purely measurement, so that is inherently corrected. It's not the same. So one other thing that so go ahead. So let's say they measured only until here, and then I put a label right across that, but it will just run straight like that. So let's say that in the higher wavelength range that there is not much of a problem. Anything you notice in the lower wavelength range? The differences?
Start at 250, it drops off.
Yeah. So the calculation seems to be just hobbling along here, and then this one within the measurement it actually goes up, and I'm not really surprised by that, because And then this was the input spectrum that we had, that we could use. But we kind of expected that even at lower wavelength ranges, there would be more water absorption, and more water absorption would cause this kind of tail in the real part of the refractive index. So this tail here, this trend here, is just caused by some huge absorption peak that is living here that we did not have available in our data. So even that was quite reassuring in a way. It's a little bit strange if you get data that seem a little bit at odds with what you predicted, but still I was kind of happy with it.
Does it also mean that the lines were in real life lying a bit higher?
Yeah, that is a good question, and that is that's a very good question. So, funnily enough, I'm pretty sure that we did the measurements. Okay, we invested a lot of time in a lot of effort in getting these reference measurements right, just to scale them appropriately. So there, I think we are on the right side. So I think this is the shape of this curve is perfectly acceptable. I do think that it should be lower, but that is I cannot prove that. That is
Maybe they use really warm blood.
not everything is specified in the papers. That is yeah, you're right. Yeah. So
Check that with different temperatures.
yeah, but so this okay. This is again a bad joke. This is why I don't want to do that anymore, because all these experiments, these experiments are done on blood of pigs. That blood of pig of a pig is very similar in specifications as human blood. Using human blood in experiments these days is almost not possible anymore. To fill in a lot of information grants, information and motivations. So you can almost not get it. So pig blood is then the second best option. But still, these experiments are very. A lot can go wrong, and this went wrong. So we had this beautiful. Maybe you can see that. So this is a water bath that keeps the blood on the right temperature. So we did not vary the temperature, but at least we had it fixed. So that this bath water bath is that, and then the blood is pumped through this device here, which controls the amount of oxygen in the blood. And then there is tubes going through the optical setup, which you cannot really see, but that's in the back, and then the measurement is done. But one, yeah. So at one time, this one of these tubes burst just while I was trying to adjust some setting of the system, and then I was covered in blood, and then I had to get back home.
Looking like a murderer.
Yeah, yeah. So that was a little bit strange. Conclusion of this part. You remember this graph, right? So where the particle radius is here on the horizontal axis, the scattering cross section is on the vertical axis. We defined three regimes. So the very small particle regime, so the particles that were smaller than wavelength, could be described by Rayleigh scattering. When the particles were much larger than the wavelength, it was geometrical scattering that only depended on, as the name suggests, only depended on the size of the particle, and everything in between, or basically everything, as long as the particle is spherical, can be described by me scattering, by me theory. The input of the geometrical scattering is only the particle size. There it is not so important, but for the other two, for me scattering and for Rayleigh scattering, you need the refractive index, the real part of the refractive index as an input. So it is one of the But it is one of the next to the size of the particle. The refractive index is one of the important parameters that determines how strongly light is scattered. On the other hand, we have the absorption. So let's take a red blood cell with the hemoglobin, the oxygenated hemoglobin, with the spectrum that is associated with that. The absorption coefficient of the solution inside that red blood cell is directly related to the imaginary part of the refractive index. And these two particles, so we have absorption on one hand related to the imaginary part, scattering related to the real part of the refractive index. So the two dominant, most important properties that describe light scattering, what we've seen is that they are part of one complex property, the complex refractive index. And causality shows us that these two are related. So if you know one, within limits, within ranges, within measurement capabilities, if you know one, you can calculate the other one. So that is then the rationale for the really bad joke that I started out with. So the refractive index really is the one property that rules them all. If you know the complex refractive index, you can calculate in principle the absorption and stuff. Then you know how the light this reflection will unfold. Okay, this is what I just said. So I'm not going to repeat that. You can look this list up yourself. Okay. In view of the time and in view of the fact that it is already Friday afternoon, I do want to make a small start with the next topic, because otherwise I'm getting a little bit nervous about the time. My proposal is to have a 10-minute break, and then maybe 45 minutes more of me introducing the new topic, and then we'll call it a weekend. Is it cool? Yeah. Okay.
Volgens mij zijn het ook wel speciaal assignments voor deze. Dat is dat ook raar. Misschien iets erboven.
Ja, oké. Maar dan, ik weet niet echt smakjes of zo. Beneden is het gewoon echt met zo'n vraag van, wil je een cookie en cream en zo? En dan betaal je wel €2. En dan ook weer de andere willen. Ik kan het studenten pas in Oh, kijk, nog steeds mijn studenten daar niet binnen. Ik weet niet. Het verschil. Ja, want ik was nog de eerste dag van de studententijd. En ik heb echt even Dirk geprobeerd mee. Oh, maar je hebt voor jullie niet pas. Ja. Het moet ook gaan
Aan deze deur open.
Nou, zou maar even grappig doen. Nee, deze ging niet. Zou je dan hier echt een beetje op het van was? Ja, de meeste van ons ook wel smaak. Maar als je hier zijn, dan zijn we niet in iemand. Dat weet ik niet. Ja, ik heb al beeld gezien ook nog hoe als het binnen is. Het is ja, ik kan een paar weken doen. Ja, maar die mensen hebben met
Ja, die had ik wel.
sommige mensen hebben dat bij mensen gehad. Oh. En mijn is dus niet van die filmpjes, dat is ook niet roos. Ja, want bij de baan is het gewoon niet. Oké, dat is waar.
Ik heb een mailtje van die van hoe ik aan moest vragen.
Oh, echt?
Heb je dit gedaan? Misschien niet aanvragen, misschien groen.
Oh.
Dat is niet voor die andere kant.
Ja, heb je ook een mail gehad?
Ja, ik moet een nieuwe halen.
Oh,
Ja.
Ik dacht dat ik niet voor jou, maar dat is herkenning. Dat niet goed.
Ja, ik
wanneer heb je een mail gekregen? Oh, ik niet. Maar de artsen is die nieuwe dan?
Ja, geen idee.
Die andere werkt toch gewoon?
Ja, dat dacht ik ook. Oké, maar wel weer goed op.
Staat er nu een naam?
Ja. Blijkbaar.
Ga die voor mij even checken wat staat er. 23. Dat is niet mijn info. Ja. Misschien nog veel uit. Oh ja, en die is nieuw. Ja, daar heb ik maar wat aan vast. Dat moet nooit naam of zo. Nee, ik kan gewoon altijd voor die vraag bij. Ja, ze zijn helemaal hetzelfde jaar begonnen. Wij zijn hetzelfde jaar begonnen, toch?
Ja.
Dus voor mij is het 23.
Ja, ik heb geen idee. Ik heb het niet.
Misschien.
Ja, leuk.
Ja.
Nou ja.
Dit hier.
Nee, hier.
Ah, dat is fire.
Hoe zijn jij dan weer dan? Nee, ik denk dat we ook niet nodig. Je hebt het ook niet nodig. Ze hebben gewoon gepakt met iemand anders en hebben niks verteld.
Kijk, dat is een verkorting.
Maar ik heb kort.
Die stedenkaart.
Ja. Dan moet je ook niet dat zeker.
Die stedenkorting. Het maakt het goed.
Echt?
Ja, heel veel.
Ik heb het. Ja, maar vragen staan ook echt bij studenten. Dan heb ik echt nog nooit gehad dat ze dat bij studenten.
Wat laat zien.
Shall we continue? I want to switch gears a little bit, leave the topic of causality behind us now, and then I'll look a little bit further at the scattering of light by tissue. It is a complicated problem, scattering of light by tissue. So what we try to do most of the time is to have model systems, some modeling that can mimic basically numerically or experimentally how that interaction behaves. And one of the simplest ways of doing that is by taking what is called discrete random media. So that means beads, spheres of a specific size and a specific concentration that we can measure, and then hopefully that will give us some insight. So I want to, for the next two classes, I want to explore that avenue. Go down that rabbit hole and see what we can learn from that. And in the first part, I don't think we'll finish it today, but we'll see how far we get. Is so-called pair correlation function. Have you ever heard of that? That is just an open question. I can understand if you have not. But, okay, good. No problem at all. So again, in the scale of things, we have to think about where, in what scale we are looking at these interactions. So we have taken a brief look at dipole interactions when we looked at brain scattering. We have also took a brief look at the cell size when we talked about the me theory. And we'll do it again, but for now, we'll be looking at this larger scale. So at vasculature scale, at bulk tissue scale, or in the model parlance, collections of particles that describe a larger volume of tissue. Just to recap, the properties that we discussed for light scattering. So these were properties for single particles. We had an expression for the scattering cross section. Do you recognize this equation? Do you know what the terms in this equation are? So what is K, for example?
K, is that? K.
What's K?
Wait,
Yeah, which it was defined as
2 pi over lambda.
So that is directly related to the color. Okay, that's fine. What is S squared? I don't expect you to know it, but just to look at the equation and emphasize that is also good. Just give me something. What would S squared?
What the reducing function?
It has arguments theta and phi, so that has angles. So it describes how the light is redistributed into given angles. So how it's basically scattered away. Then we have sine theta d theta d phi. That's the integral. That means that we sum over all the angles. So it will just tell us how much light how the light is scattered over all different angles. Scattering cross section, does it have a unit?
Yes.
Yeah. What is the unit?
Meter squared. Not per minute.
Settle on one. Can you settle on an answer? Can you settle on one answer? It's a cross section, so it is meter squared. So we had a couple of so do you remember which properties we had to describe the absorption or scattering by one particle by one molecule? We had, obviously we had the cross section, so that is the let's call it the sigma. We had two more.
The efficiency and the coefficient.
Yeah, the efficiency, so that had symbol Q, and then the coefficient of that symbol U. So what was the relation between the that's one I'm after out. What is the relation between the efficiency and the cross section? What are the units of all these three properties?
The unit of the efficiency is 1.
So just a number. What's the unit of the?
And the other one is 1 over.
Yeah, 1 over length.
Because
So
this is
meter,
the-
centimeter, whatever. That's all fine. And this one was. You just said there. So square. or area squared meter. So what is then the relation? What was the relation between these two? So the efficiency Q and the cross section.
It's like the efficiency multiplied by the geometrical cross-section.
Yeah. So the geometrical cross section of the particle itself or the molecule itself. So sigma is Q, which is dimensionless, times a geometrical cross section, which has, of course, dimensions. Square meter. And then it works out. Okay, scaling up to the coefficient is a little bit more complicated. That's the topic of actually the topic of today. So I'm not gonna go into that for this moment. But getting back to that to this equation. So now we had that. So k was the wave number. So 2 pi over lambda. So k squared has units. Multiplies dimensionless, so lambda squared. So area. So in the end, we will get something that is that has units of area. S squared was the function that describes how light was distributed into different angles. What is then the phase function?
The units of the phase function.
No, what is it?
It's normalized, so it's a probability distribution.
Yeah. So the information. So basically, you're having the same function here that you divide by two numbers. So the information is the same. If you're right, it is normalized. It is now normalized on theta and phi by this constant, and then. But it holds the same information. It holds the same information of how light is distributed over the different angles theta and phi. Okay, what is then the scattering anisotropy? G. What is G? So the answer is there, but I'd like you to explain.
I thought it was a value that implies how the light is scattered in which direction.
Okay. I would agree. Any more thoughts? Any more formal definitions? Any more?
It's on average, right?
Yeah. So these two bars indicate an average. So what the equation basically says that it is the average cosine theta. So what does that mean?
If the amount of light is being scattered in one direction.
That's the answer I was looking for. So if light is scattered purely forward, then theta is 0. And the cosine of theta would be 1 in that case. And the average cosine in that case would be 1. So G, the measure G, tells you something about how much light is basically scattered in the forward direction, and if it's purely forward directed, then you can imagine that. But let's say that the photon is scattered in this under this angle. So light's coming in from here. It's scattered at the particle. It is scattered into this direction. But here is my detector. So what part do I pick up? Yeah, the cosine. Yeah, that's so exactly the part that is proportional to cosine theta is the part that travels in the forward direction. So that's the part I will pick up. So that yeah, that's the importance of this parameter. Another few equations that you did see, but maybe a few weeks ago, we can tie the scattering cross section to the thing that we can physically measure, namely the intensity, the scattered power to the thing that we can control, the intensity. So we can express. If you look at the units, then it makes a little bit more sense. We can express the scattered power in watts as a multiplication of the scattering cross section in units of the area times the intensity control. The approach of calculating the scattered power, so the total scattered power, so not the total scattered power, was to integrate that over a let's say a hypothetical sphere. So there is a particle that scatters light. We can cast a hypothetical sphere with some radius r around that and integrate all the intensity that goes through that sphere through the area of that sphere, and then obtain an expression for that power. The idea was that if the sphere is large enough, so you don't look too close, if the sphere is large enough, then the scattered field will become spherical. So that is an approximation that we can use. We can using that equation, we can now using that approximation, we can write an expression for the scattered power looking like this. So we have a scattered power as a function of distance r, so that is how far your detector is. Theta and phi, that is from your origin point where the detector is located. Then there is I0, the incident intensity, which you can control. There's K, the wave number, which is related to the wavelength, so the color of the light that we used, which we can control. R was the distance, and then S, this unknown factor S, how the light is redistributed. We could combine these equations, of course, because we had this expression for the scattered intensity based on some unknowns and some knowns. We had this thought experiment of having a particle, putting a sphere around it, and then calculating scattered power. We can combine these two equations and then basically end up with an expression like this. So scattered power, incident intensity, the S function that we do not know, K squared, R squared, and then integration over spherical coordinates. So R squared, that is not in this equation, it should be runs in principle over 0 to infinity for R, but they fall out, so we only are left with the polar integrations. If we combine them, then the expression for the scattering cross section becomes this. So what we need to know, basically what we need to know for this to calculate the scattering cross section is we need to know the wavelength, K, what the wavelength, K, we need to know or estimate or whatever determine this function S. Okay.
Sorry,
Yeah?
you said that the R didn't matter because it falls away.
Yeah. Because so Yeah, so it should be in this equation, but essentially because this one cancels with this one, then it.
But if you integrate it first, and then you will get R from 3, will it still interval?
Yeah, it's a good question. I don't know. That's
I mean, if we integrate over a surface element, we shouldn't have a dr in there anyways, right? So we have a
Um,
the radius is necessary to determine the.
yeah,
But if we don't want a volume, and we don't want to receive a volume anyway, so can't integrate along R.
That's right.
so are you now arguing that we can cancel it or we can't cancel it?
I mean, we don't need to cancel it. There shouldn't be a dr in there anyways, and it isn't. So
Okay. Yeah, that okay. I get that one. If you look at the surface element on a sphere, that is I think r squared dr sine theta d theta d phi, something like that.
no, I think it's just r
That's
squared.
the values.
Yeah, that's. So there's an r squared in there, but no dr.
Okay.
Yeah, if you have dr, I think you're going to measure the infinitive volume of this surface.
Okay.
I think that's the right notation for the
Okay.
surface.
Oh, and then you don't have to integrate.
No, it's not.
No, so then we're, yeah, that gets me up the hook easily because the r squares still cancel and the dr should not be there. So that,
Yeah.
oh, that's good. That's very good. You got me a little bit from my apropos. So what we usually do is calculate the cross section. So this is a calculation. So the one in black here, in blue here, is a calculation that we do for a single particle. So for a single particle, we have these beautiful theories. We can calculate s squared, D theory, for example, and we would calculate scattering cross section. So we would have that for a single particle. What now if we have two particles? So we don't know exactly what the light will probe, the light will see. The measurement geometry that we use may not even care if you look at one or two particles. So how would we approach this when there is, let's say, two particles, three particles? Then what's your feeling about it? How should, so let's say the scattering strength of one particle is factor 1. What is the scattering strength of two particles?
If they don't interact with each other, maybe we can take the sum.
Yeah. So if they, and that is usually the assumption, if they are far enough from each other, if there is no interaction between the particles, then you can just say, okay, so one particle scatters this amount of light, the other one scatters the same amount of light. So taken together, they will scatter the double amount of light. And that continues along this whole process. So the scattered power would be twice the amount of light scattered by one particle. The scattering cross section would be the amount of light scattered by particles. That would just continue. Okay, but now let's take a look at the situation where this does not hold. So this was the equation for the scattered field. So let's say we have an ensemble of particles, E particles. The label E is counting on the particles. They are illuminated all with the same field, so En. They all have the same distribution function S for the electric field. The only thing that difference is their location. RE. The proper way to calculate what we would detect at the detector is the detector measures intensity. So we would first calculate the scattered field, square that, and then we will get the intensity. So the first thing that we need to do is to calculate the scattered field. Scattered field for all these particles. So again, the super subscript E is denoting of particles. So we have a field that is scattered by particle 1, by particle 2, by particle 3. The intensity is then given by that total sum multiplied by its complex conjugate, and average of the response time of the detector. That is how we get to a physical measurement. That would be the way to calculate that intensity. But let's try to investigate what happens here. So suppose n is 2, so we have only 2 particles. They both scatter light. They both do that in such a way that the light scattered from particle 1 has an amplitude E1 in phase C1. The other one, E2, scattered light from particle number 2 has an amplitude E2 in phase C2. Can you now write down the total field scattered from these 2 particles, and can you also write down the total intensity scattered from these particles? Just using, so the information is on here. But then for n is 2, how would that look?
Summation for the field.
Yeah, but then work that out, of course. But, yeah, summation is of course right. So you would have E1 plus E2, but then we will get this part. So how does that work out? Yeah. Okay. So, so E scattered in this case is going to be E1 plus E2. So what happens if you add these two? These are two complex representations of the electric field, of the scattered electric field. What happens if you add them?
We multiply E1 and E2 or add the two.
Yeah, so if you if you add the two, nothing really happens. You just add them. The trick is in this step. So you first add them. So the scattered field is E1 plus E2. Then, in order to calculate the measurable quantity, the intensity, you have to multiply it. You have to multiply the sum of E1 and E2 with complex conjugates. Okay, so, do you have an expression for that?
Get the intensity of the first field and the second field, and then the interaction between the two interference.
Yeah, the interference. Yeah, and do you also know how that interference term is written or signified?
Yeah, it's going to be the difference between the phases.
Yeah, that's exactly
and
true.
the exponential.
Yeah, so you can so E1 so the scattered intensity is going to be the sum of E1 plus E2 times E1 plus E2 times conjugated and then averaged. So the star is the conjugate and the bracket is averaging over the response time of the detector. I don't have a mathematical formulation for that, but that is physically what happens. So that is why it is there. So you can then just fill it in. We can have E1 is an amplitude times an exponential phase term of E1. Same thing for the field number 2. For the complex conjugate, we just switch the sign of the complex number, and this is just something that we can algebraic work out. Second order equation. Of course, the V1s with their complex conjugate they will cancel, so that will give a real valued result. E2 the same thing, also a real valued result. And then the last term is this long term over there. Product of E1 and E2, or E2 and E1, that is the same thing. In the product of two complex exponentials. And you will recognize that this is the very definition of the cosine, the complex definition of the cosine. So in the end, one more step. In the end, this is what we will measure. We will measure an intensity scattered from these two particles that is given by the intensity scattered by one particle, plus the intensity scattered by a second particle, and then this cross term that depends on the phase difference between two particles. What does this phase difference depend on? Yeah, that physically you can be you're right. Let's for a moment assume that we freeze the sample so that all the particles are stationary. The speed of light is as it is, very fast. So the time is not the length to the detector, because so the positions of the particles is what is going to determine this phase difference. And if they are far apart, then it can be a long phase difference. If they are close together, it can be a short phase difference. So formally, if we have n is 2, then it would imply that the scattered intensity at the detector would be the intensity from particle 1, from particle 2, and then this cross term. But in reality, in tissue or And the other sample, we never have just two particles. We can have two particles, but they are sometimes we measure two particles in this configuration. Sometimes we measure two particles at that configuration. And then the averaging over the detector response time takes place. If you would do just a single snapshot measurement of two particles, then we would need to use this equation. But in general, we would measure an ensemble of, let's say, two of these particles in different configurations, and these relationships, these phases would average out. So we would not see them anymore. It would be random in time. So this whole average of cosine delta phi, in effect, is not present. And that means that if that term evaluates to zero, then the scattered intensity would just be the intensity of E1 plus E2, so of the two particles together. And that is what we will measure. And then if you use the same reasoning, you can extend this to three particles, to four particles, or more particles. Then, yeah, if all these differences, if they just keep averaging out, then for many particles n, the intensities would just be the sum of the intensities of the individual particles. So the totals, in this case, that means that the total scattered intensity here on the left-hand side would be just n times the scattered intensity of a single particle, if the particles are identical. So we can manipulate a little bit with that new knowledge. So if that goes for the scattered intensity, it also goes for scattering cross-section. You remember that the scattering cross-section was calculated by taking the scattered intensity, integrating that out of that huge sphere with a huge large radius. So you can do the same thing, but now with two particles centered in the sphere, n particles centered in that sphere. So we can do the same thing. So we can calculate not only the scattered intensity, but also the total scattering cross-section that way. That would just mean, by means of the previous arguments, that the scattering cross-section is n times the total scattering cross-section is n times the scattering cross-section of the single particle. Does that make sense? That is the part in the blue box. I've made the equation a little bit more complicated because I can use that later on. To include the phase function. So the phase function describes how the light was distributed in the different angles, but also, so that is P of one particle, but also the integration here over sin theta d theta over phi, which is implicit, because of the 2 pi, already implies that I've taken that into account. The normalization of the phase function was the normalization property of the phase function was that it was 1. So adding this is basically a trivial thing to do. Just adding a factor 1. I'll need that later on. I'll keep it. And then the last point is the scattering. So this would be the total scattering cross-section of n particles. So just adding n of these particles. The scattering coefficient, so if you like, the density of scattering cross-section is calculated in this way. So you take the total scattering cross-section obtained in this way, divided by the volume in which the scatterers are located. So that would be working out. The denominator would be n times the scattering cross-section of one particle, n divided by v is the density rho. So then this equation. Now, of course, a long time coming in this whole argument is that this whole cancellation of phase terms is not always going to work out fine. So the assumption that the average delta phi, the average phase difference between two particles, is going to be 0 is justified by randomness. So if you place a particle here, if you place a particle there, they will have a phase difference, of course, if you measure only the two. But you can always place another set of particles with some other positions that will generate the same phase difference, and that will then cancel the first value. So that is usually the reasoning by saying, okay, this is not so important. The question that I want to ask, or that I want to study is that allowed? Can you actually say that, or there is it justified to fully cancel all these phase terms, or is it not justified? And if it is not justified, then we have to take that into account if we calculate the scattering, the total scattering cross section, or if we calculate the scattering coefficient. Okay. This is an obvious example where this will not be the case. If you look at the crystal, then the scattering centers, the scattering have a fixed place. They cannot move. So if you illuminate the crystal from with light from one side and you detect from another side, there is a fixed geometry. Incident light excitation, light angles between scattering centers and etc. So there the argument of averaging out will not hold. These scattering fields from these different particles will interfere. So you will see that in the detected intensity, and in fact, you can actually use that to characterize the crystal. Waar ben je precies uit? Oh, naar beneden. Dan moet je even naar rechts en dan is een trap naar beneden. Oké. Dat zullen we allemaal wel. Get out. So these scattered fields from these particles, as well as thin crystals, are interfering, and you can use that to characterize the crystal. Do you know what, maybe from another course, how that is called? Yeah, so the process of illuminating the crystal with one angle, then measuring under another angle, you measure some property from the crystal, and then that is used to characterize it. It has a name. I was just curious if you heard it before or not. Okay, the structure factor. Yeah, so it tells you something about the structure. But we'll get to that. We'll get to that later. Now, suppose think of tissue, as in the cartoon here, a tissue that can be healthy or malignant, so changed in structure. But let's assume now that it has only one dominant scattering center, so only one dominant way of scattering light. That means that we can model it as this, let's say, collection of marbles. And like the crystal, when these particles are aligned, well aligned, then the interference of these scattered fields can in principle be calculated if we have some kind of description of how they are positioned, we can calculate how it scatters. This is the last thing. This is the last thing I want to do for today. I was looking forward to it, so I'm still going to do it. This is a movie that I made from at conference 2 years ago when we still had conferences, and this is just people entering the room. So they're just trying to finding their seats and going to sit. I was in another time, in another place, I would have you ask to leave the room mentally or physically. Think of a row that you would sit in this room, and think of a seat number that you would sit in this room. Okay, so let's do the experiment very quickly. You would go out, you would go in, you would have to think of a row number and a seat number. What would happen, do you think? I mean, this is a small group, so nothing much, I guess, but what could happen?
Somebody at your seat.
That's of course. So if you would do this experiment with a large group of people, then probably this would be the situation. So you would have seats where there is 3 people, where there's no people, and there's 5. Just randomness. So now let's take a look at the statistics of this. And so let's say that we know that the number of people that are going to fit in this room is X. The number of chairs is N, and sub C over there. So we can calculate the global density X over N. That is the average number of people in a seat. So no strings attached yet. So now let's also say that there is N chairs in each row. So we can also estimate the average number of people that are going to be in a row. So that is N times that density times that row. Great. Still more people trying to find the exit, I think. But that's. We're supposed to be at the hospital, but so this would be the simulation, the situation. If we would do this randomly, if you would repeat this experiment many times, then you would see that the number of people per row, so let's call that K, variable K, will follow a Poisson distribution. So again, there is no strings attached. Everyone can sit whatever they like. They just think of a row number, a seat number, and we'll see what happens. That will follow a Poisson distribution given by this equation. So we have average XR per row, given in the box here. So n times the density. We have K as a parameter. The link that shows that this actually is true is here. This distribution has a few interesting properties. The first is that the average number of people per row, which what we were calculating, is going to be n times the density. So that means that it is going to be equal to the global density. That makes sense. If you have a big room with a lot of chairs, a lot of people, then the average number of people per row is going to be equal to the overall average. The variance of the number of people per row. So the variation around the mean has this expression. So do you have a good feeling of about what the variance is? So you have a mean, a standard deviation, so that's the fluctuation around that. And the variance is the square of that. So for this distribution, we have the property that the mean and the variance basically are the same. So if you have a large but limited number of seats in a room, you keep putting in people, then the average number of people in the row will increase, of course, with the variance. So the number of people will increase as well, and they will increase in sync, in size. So expressed as densities, that means that the average density in the row is going to be equal to the global density, but the density variance in the number of people per row here is also going to be equal to that same density. This is all by because we allow some seats to be empty, because we allow some seats to be filled by 5 people. Of course, this is not at least in this experiment, not a feasible question. And it was all connected to the fact that okay, this liberate way of filling the room connected with the Poisson distribution. If we use a more realistic situation where only 1 person per seat is allowed, then we cannot use the Poisson distribution anymore. Do you know what distribution we should use in that case? So restricted, let's call it restricted seating, so only 1 person per seat. Yeah, that's a very good point. So binary kind of function.
Binomial.
Yeah, binomial. That's binomial. So the start is more or less the same. We have still X people that we want to fit in the room. We have still and sub-C chairs that we can use, and the density, even if it is completely filled, will be rho. We calculate it like this. It also means that the probability that a chair will be filled, a single chair will be filled, is given by X over M. If that row in the room has n chairs, then the probability of having, and this is the binomial distribution, the probability of having k of them filled and n minus k of them not filled is given by this expression. And then we have a few ways of organizing that. So we have n chairs in that row. And we want to fill that with k people. So the number of ways of doing that, the number of distinct ways of doing that, is given by the binomial coefficient n over k expressed here. So in the end, that means that the probability of filling k chairs in that k out of n chairs in that row is given by the binomial distribution, like this. That binomial distribution also has a few properties. interestingly, the average number of seats in this case, or the average number would be n times O, just like we had before, just like the global average. The variance, however, is not the same. So that is now not is not. So it was for the Poisson distribution where everything was possible. It was the same as the mean. But now we have n times rho times this additional factor. So basically, what this means is that if we increase rho, if we increase the number of people in the room, then because only one person can sit at the same seat, then the variance of the number of people sitting in a row is going to decrease. Ultimately, if there is only a few people, then the variance can be high. If there is a lot of people, then every seat is occupied, and the variance will also be very low. So what that means for the basically the same graph. So where we had a mean and variance of the number of people per row versus the total density of people that we are going to put in, the mean will still increase. The average or the variance, the variation will depend on. Will basically depend on how much we try to cram this system. So what is the relevance of this? And this is my last remark for today. What is the relevance of this? We started out with two particles. We could calculate the phase difference between two particles. Translated into the intensity, so the thing that we can measure, and then the line of reasoning was okay that if we have two particles here, two particles there, it will average out, and in effect these phase differences do not measure. That only works if you can actually find these two pairs of particles that cancel out. If there is some kind of organization, if there is some kind of relation that puts particles into places, or that dictates the organization, if it is not totally randomized, then that may not work. Then these phase differences will not cancel. And then we need to find some way to actually incorporate these differences. So they may not be cancelled. So and that would immediately imply that what we did before, that the total scattering cross section is not does not sum up as the sum of the individual cross section, and that also implies that the scattering coefficient may be a little bit different. So that is the. Just quickly seeing what my next slide is. That is what I want to explore on Tuesday further. So the extreme case again is a crystal. So there is nothing random. Everything is organized. I'm not going to go into that. But we can have a kind of an intermediate case where we have particles that are inside the tissue, but that their positions are not completely randomized. Can you think of one reason why that could be? That is then really the last question. So let's say I am going to model tissue as a collection of marbles, of knickers, of let's say 5 micrometer diameter, because that is about the size of cells. So I'm going to just put them into a fluid, and that would be my model for tissue. So is there any reason you can think of why all these particles, these marbles, could not take up any random position at all?
Not enough room.
Okay, no. Could be. That's good. That's also a good point. Yeah, so that's both good.
Interactions between the particles?
Yeah, what kind of interaction could that be?
They stick together.
Yeah, excellent point. One more obvious point is that these particles have given size. So they can touch, but they cannot overlap. So mathematically, this position would be just a number in some kind of 3D space. But in effect, it cannot happen because if the particle is 5 micron in size, then two particles can never be closer than 10 micron. So that's also happening. But we'll go into that. I think it's way too much for the Friday afternoon by now. I wish you all a very, very good weekend. Just one final remark of the assignment. I think you all, I guess you all submitted it, right?
Our group is submitting it.
Okay, no worries. So I'm not. So I had to submit a deadline because otherwise I could not put it on Canvas. So that's why it is there. So take
It'll be there for time.
Yeah, that's good. I will try to have it back for you on Tuesday.